Okay, we'll take a few minutes to discuss number 3 from the 2012 AP Calc AB free response set. And this is the first problem from that exam that you were not allowed to use a calculator in. And they give you this graph of a function f, and they say that the graph is 3 line segments in a semicircle. So they've provided you with a few points here so that you're going to be able to do the necessary geometry a little bit later on whenever you need to within the different pieces of this problem. And in part A, they want us to do two things. They want us to find g of 2 and g of negative 2. Well, if you read the problem carefully, g of x is defined right here. This is a graph of f of x. Now, the way that g of x is defined is that it definitely depends on the graph of f. But if we wanted to find g of 2, just like you'd normally do, you want to take a function and evaluate it at a given value, take the given value, put it in place of the x, that's what I've done in the definition of g, and then evaluate. So the definite integral from 1 to 2 of f of t with respect to t is all g of 2 corresponds to. Now if you're going to compute this, if you use area arguments, that would be a triangle right there, and a definite integral corresponds to the signed area between the curve and the x-axis. So this integral can be found just by taking the area of a triangle. So this triangle has a width or a base of 1, and then if you define this to be the height, if you think about a rise of negative 1 and a run of 2, that would be equivalent to a rise of negative 1/2 and a run of 1. So this dimension right here on this triangle is going to be 1/2. Using the formula for the area of a triangle, you can determine that the area of this shape is going to be 1/4 square units. Since it's below the x-axis, we need to make it negative since a definite integral corresponds to signed area. Now when you go to find g of negative 2, it's quite a bit tougher because g of negative 2 obviously is going to account for more area between the curve and the x-axis. But just like we did before, put negative 2 in place of x in the function. Now, to use area arguments the way we like to use them, we need the limits of integration to be in the proper numerical order. So we'd rather have the smaller numerical value as the lower limit of integration. You can always flip your limits of integration as long as you hang a negative out in front of the integral. So that's what I did here. And then I realized I would have had to find the area of this semicircle, and the semicircle has a radius of 1. And so its area is going to be half the area of a circle, and put 1 in place of r in the formula for the radius of a circle, and you get pi over 2 square units for the area of that figure. And then the area of the triangle that we see right here. Now this triangle has a height of 1 and a base of, a height of 3 and a base of 1. And so if we use 1/2 base times height on that, we get 3/2. Now the only other catch is that this area that turned out to be pi over 2 square units is below the x-axis. So we have to make that negative whenever we're putting down our answer for the definite integral. And then this is above the x-axis, so it stays positive. And then if you distribute the negative in that we had to involve in order to switch the limits of integration, you end up with this for the value of g of negative 2. As we move on to part B, we're asked to find g prime of negative 3 and g double prime of negative 3. Now before you can find either of these, you're going to have to start with some derivatives. So if you're taking the derivative of this function right here, what's useful to use is the second part of the fundamental theorem of calculus. And I have from our notes what that was defined to be. So this is from right out of our book. So if f is continuous on the closed interval a to b, and you define this capital F function to be a definite integral with x as the upper limit of integration, then the derivative of that function is just going to be the integrand that you have here with the upper limit of integration replacing the t. And so what we usually did was we thought of this as a derivative formula. So if we're taking the derivative with respect to x of this type of function, all we're going to do is put the x in place of the t, and that's our answer. So when we move back to that free response question, if we want to find g prime of x, we're going to take this x, we're going to put it in place of the t, and that's going to be our derivative. So g prime of x is equal to f of x. And if we want to know g prime of negative 3, well, check out what f of negative 3 is. So if you go to -3 on your x-axis and then go up to your graph there, using a rise of 2 and a run of 2 to get from this point to this point, you can say, well, that's equivalent to a rise of 1 and a run of 1, meaning that this value right here is going to be a y value of 2. So g prime of -3 is going to be 2. To find g double prime of -3, we're going to have to start with g double prime of x. Well, if g prime of x is equal to f of x, taking another derivative on the left gives us g double prime. Taking another derivative on the right gives us f prime. So g double prime corresponds to f prime. So basically, being asked to find g double prime of -3 is just like being asked to find f prime of -3. Well, since this is a line segment here, and a derivative represents the slope of the tangent line, we're going to be able to use the slope of this line segment for the value of f prime of -3. So again, you can use rise over run to figure out that that has a slope of 1, or if you wanted to use the slope formula, difference in y over difference in x with these 2 points, you get 1 either way. So g double prime of -3 is 1. Moving on to part C, it wants us to find where the graph of g is going to have a horizontal tangent. So a horizontal tangent is going to happen any place where the slope of the tangent line is 0 or where g prime of x is 0. Based on what we did in part B, we know that g prime of x equals f of x. So if we want to know when g prime of x is 0, we can just look at this graph and try to determine when f of x is 0, since those two functions are equivalent to each other. And so g double prime of x is going to be equal to 0 right here, where f of x is 0, and again right here, where f of x is 0 for a second time. And so g prime of x is 0 at -1 and 1. Since this graph of f really is a graph of g prime, since they're equivalent to each other, f prime is positive to the left of -1 and negative to the right of -1, meaning that g of x goes from increasing to decreasing, positive derivative to negative derivative as we cross this value, leaving us with a local max. And then at this other critical number, at 1, the value of g prime is negative to the left, it's also negative to the right. So even though our graph does have a horizontal tangent at x equals -1, we have neither a local max or a local min there, because we don't change from increasing to decreasing or from decreasing to increasing. And then the last part of this, part D, wants us to figure out, based on the graph, where this function g has points of inflection. So a point of inflection is going to happen anywhere where you have a change in concavity. And concavity is determined by the value of a second derivative. Well, in part B, we computed the second derivative of g. G double prime was equal to f prime. And so if you look at this graph of f and thought about how you determine values of f prime, you'd hopefully recognize that, well, the derivative of a graph is always going to represent the slope of the tangent line to that graph. So f prime is positive here because of the positive slopes for the tangent line, negative here, positive here, and then it's back to being negative there. The slope of the tangent line to this graph tells us values of f prime of x, and in effect, values of g double prime. So where does g double prime change signs? Well, it changes signs at the x value of -2. It changes from positive to negative. So our function g, its graph is going to change concavity from concave up to concave down as we cross -2, making it an inflection point. The slope of our tangent line changes from negative to positive as we cross this x value, and that would be the x value of 0. So we have another inflection point at 0. And then the last inflection point is at 1, because our tangent line slopes go from positive on this little interval right here to negative on the last line segment that we have graphed. So we have 3 points of inflection for this graph because the slope of the tangent line to f of x changes signs at those locations, and thus g double prime also changes signs in those locations.